Hi, back to Basic Electronics Series 2. Or you look back at the Basic Electronics Series 1, are probably gonna follow some topic that I mentioned earlier. What I'm going to talk today is about our signal sources, and then also talking about our capacitor, inductors, applications in the term of filter circuits. Okay, let's take a look at the signal sources. In general, we have signal or sources that includes our signal generators, power generator, function generator, and you're probably familiar, with that already. I just mention about it again. Signal generators, sometimes you use some like sine wave for circuit testing or circuit analysis, and power generators is talking about the waveform look like this one here. So you associate with the power with amplitude period. Also polarity, talking about the rise time and then the fall time. The last one is function generator that can generate sine waves, triangle waves, square waves, etc. That you can vary your amplitude or frequency, and we will get into that later on. Since the last time we talked about resistors, that's when you apply Ohm's law, V equal to IR, and you know exactly that I simply equal to V over R, and R doesn't change with any kind of frequency or whatever that changing with time. So that's why I introduce sine waves. That's the have for frequency in the term of omega. It's come to play around with. And then let's start with the capacitor. When you're talking about our AC signal, usually it's not gonna play any important roles in a DC circuit. But when we're talking about AC circuit, that's dealing with frequency and amplitude. We will see the effect of capacitor, and also later on we talk about inductor. Capacitor is coming in the term of the unit of farad, and the symbol like this one. And they have so many applications. You can use capacitor for filtering, for blocking any kind of signal that you don't want, and also bypass applications, and so on. There are still much more that I haven't mentioned at this point. And you can also use capacitor in circuit. For example, differentiator, integrator, filter circuits. That's in this YouTube series. I will get into details. And the very simple equation for capacitors is the Q equal to C multiplied by V, when Q is the charge in the unit of coulombs, C is the capacitance of the capacitor in the unit of farad, and V is the voltage in the unit of volt. For example, you have the parallel plate, you have the conductor, and between you have dielectric material, and two conductors, plates separate by D, and the upper conductor plate you have a positive charge Q on the plate, and the lower one you have a negative Q. And you know a simple equation to calculate for C or capacitance is equal to epsilon A over D, when epsilon is permittivity of material between conductors plates. A is the area of the conductor plate, and D is the separation between two plates. And also, if you want to calculate for current flowing through C, they have a basic equation: RC equal to C multiplied by dVC over dt, or the voltage change with respect to the time. And you can see when you use like the differentiate, for example, if you have Vc in the term of sine waveform, let's say sine omega t, and you differentiate sine omega t with respect to t, you're going to get our cosine, and that's mean you have the difference between sine and cosine function. Just like 90 degree out of phase, and since the sine start from here, when let's say omega equal to 0 here, sine start from 0, where cosine start from 1. So it's look like function cosine is leading the sine function for 90 degree, correct? Because at the same point when t equal to 0 here, or let's say omega or t, but you just take a look at the function of sine and cosine. At t equal to 0, sine equal to 0, and when t equal to 0, cosine 0 equal to 1. So it seems like this one is shift ahead of sine function. So that's why we call, when you differentiate current, you differentiate the voltage, for example function sinusoidal, you get a cosine function. So the current will have the phase 90 degree, or we say like 90 degree different, and it's become a leading phase for 90 degree when you compare it to the voltage. The other thing that you need to consider is that when you're talking about R, you know that power dissipation across R is P equal to IV, or let's say I square R, or even V square over R, correct? Power dissipation across resistor is going to turn out to be in the term of heat. So that's why you have like higher temperature when you pass the current through a resistor. But for a capacitor, you would be surprised that you have no power dissipation across capacitor, but instead it's going to store the electric power into capacitor. It's just like water tank. You fill up water in the tank. When you have the water flowing into the tank, it's the same thing as capacitor. When you have the current or the voltage change, or you have the current flowing through the capacitor, it's gonna cause the voltage of C is rising. And when you disconnected the current source, the voltage starts dropping, or we call it discharging. For this equation, you can say that when you have the change of the voltage to be 1 volt across C 1 farad in the time 1 second, is cause the current in a capacitor 1 amp. Okay, Or if you consider the current equal to 1 amp and C equal to 1 microfarad, that means in 1 second you will have the voltage increase in C. It's about 1000 volt per second. Okay, you can substitute 1 milliamp in here, and you have substitute C, that's equal to 1 microfarad or 10 to negative 6 farad, and you divide 1 milliamp by 10 to the negative 6, you end up with 1000 volt per second. That means you see going to have the voltage increase 1000 volt per second. That's how our capacitors work. Now let's take a look at application of a capacitor. This is just for information for non-critical circuit application. You probably use minor types of capacitor. There are so many types of capacitor. If you want greater capacitance, you need to use our tantalum type of capacitor. Or you want to use for power supply filtering application, you're just going to use electrolytics. That's in the form of metal foil with oxide insulator inside. Okay, this is just for different type of capacitor. Now before this, we take a look at when you talk about R in parallel and in series. You can find R total. And now what about capacitor in series and parallel? This is the way you connect C in series. You will be surprised. C total is going to be some kind of opposite the equation of R total, because R total, when you connect in series, you just simply add up R1 plus R2 plus so on, and then plus Rn. But for C in series, 1 over C total is going to be equal to 1 over C1 plus over C2 plus so on, and then 1 over Cn. And in parallel, you simply add each C up, so C total becomes C1 plus C2 plus C3 so on, and then plus Cn. Okay, now take a look at this one. Why does it look like this one? Okay, I mentioned earlier that equation, the other equation for C is the total charge on C is equal to C multiplied by V. When you connect C in series, look at this one here. The total V start from the leftmost to the rightmost. I put that as V, and each C has V1 across itself, so V equal to V1 plus V2, and you apply this equation, Q equal to C multiplied by V. So your voltage here is simply become Q over C. And if I look at the whole circuit like this one, C total with the voltage across capacitor to be V, I have V equal to Q over C total, and V1, you do the same thing, become Q1 over C1 plus Q2 over C2, because this is the represent V1, right? And this is represent this is represent V2, this is represent V1. Since you have no other connection to the circuit here, you will have the same chart on both C1 and C2. So Q cancel out. You end up with 1 over C total equal to 1 over C1 plus 1 over C2. And that's how you get the C total when you connect C in series. Now it's same thing as in parallel here. You consider y C total becomes C1 plus C2 plus C3, so on, and then plus Cn, because you have our total Q equal to our Q1 plus Q2, and Q, you apply equation Q equal to C multiplied by V, and when you connect C in parallel, they all have the same voltage, right? So that's why I wrote down as VVV, and C total multiplied by V equal to C1 multiplied by V, and then you can divide on the left, the right application, by V, and then you end up with C total becomes C1 plus C2 plus so on plus Cn. Now from this equation, the current flowing through capacitor equal to C multiplied by the differential of Vc over dt. Take a look at this one. If I supply the current 10 milliamps to the circuit, your voltage across capacitor start increasing, and then or this stage we call a charging stage, right? And it will reach the maximum voltage and it will stay there. It doesn't increase anymore. Okay, so this is become just give you an idea about how capacitor work. And then it's just like I mentioned before, when you're talking about R, you have power dissipation. P equal to IV, it's turned out to be your heat. But for capacitor, it just become store energy in capacitor. And then you can use that as the voltage source, for your circuit, because you have electrical energy, stored in the capacitor. Now for our circuit analysis, or the application of our capacitor, take a look at a simple circuit. You have R in series with capacitor. You have current flowing through the circuit like this one. So you can use equation, or I that's flowing through C and through R, they are the same because this is in series. And then for IC, you simply apply C dV by dt, and of course it's going to be equal to I also pass through R. This means your I pass through R, since the R and C has the same voltage because they are in parallel. So this has become I passing flowing through R, and this is the current flowing through C. And then you want to solve for your output Vt. This is the basic calculation. Basic calculus. And then you divide dV by V, and you move dt to the right. You move C to the right. So it's become dV over V equal to -1 over RC multiplied by dt. And you integrate, these two equations here on the left and on the right. On the left, you're gonna have like ln V over V0, when V0 is the constant from integration. And on the right, you have this is constant. You simply have you have T show up. You rearrange the equation here, become V over V0 is going to be equal to exponential of -1 T over RC, right? And then you simply multiply exponential term with V0, and you end up with V0 here. Sorry, missing V0 here. And this one here, RC, we call time constant. Of course, as I told you before, exponential you have no unit, so your RC has to be the same unit as the time, so RC is going to end up with the unit of second. RC become constant. Now you take a look at the plot uh, between the voltage at the time here. When we end up with equation Vt equal to exponential or negative t over Rc, we have our capacitor discharge, or the voltage decreasing with the time. And if your Rc is big, that means your capacitor will discharge quick. Okay, so that's tell you about how fast your voltage across C when you have no sources we were decreasing. And for the time equal to Rc, this simply become exponential negative 1, and that's give you a 0.37 at 37%, or let's say when your time equal to Rc equal to time constant, your voltage going to reduces to be 30% of the original voltage, or V0 here. Let's say when you have R equal to 1K, C equal to 1 microfarad, your time constant, or Rc, is going to be 1 k ohms multiplied by 1 microfarad. It's give you 1 millisecond. So if your voltage to be 1 volt, then your current is going to be 1.0 milliamp, because you can use this relation here. Okay. Now take a look when you have R in series with capacitor, and you have the voltage source here as Vn. You close the switch. Your RC current flowing through a capacitor is going to be equal to C dV out over dt, or simply when you have V out here, your RC, this is in series, so I flowing through R is going to be equal to R flowing through C. Your IC also equal to V out minus V in and divide by R, because they have the same voltage here. And you saw equation, so you do V out, you move this one to the left, and you move C to the right. You have the V out over V out minus V in equal to 1 over RC, and you integrate both sides of equation. You have ln V out minus V in over V0, and V0 is the constant from integration. And on the right hand, you simply have only negative 1 over RC, and then multiplied by dt. dt here. And you rearrange the equation. Your V out minus V in is going to be equal to V0 multiplied by exponential negative t over Rc. Okay, it's the same thing as the previous circuit, except here you have V in. So if your V in becomes 0, you get back to the previous circuit equation. And then V out is going to be your V in plus V0 multiplied by exponential negative t over Rc. If at the starting point at t equal to 0, you have V equal to 0, So you simply get the equation here. V out at t equal to 0 become V in. I'm sorry, V out here becomes 0. This is 0. And your V in 0 equal to V in plus V0 exponential negative 0. So this gives you 1. So you have V0 equal to negative V in. And you simply put V0 in here in the term of negative V in. So you have V out equal to V in multiplied by 1 minus exponential negative T over RC. So it's become V out for the circuit here. You can repeat by yourself. Same when the time equal to time constant, you have this term to be 1. So 1 minus exponential negative 1 is become 1 minus 0.37. So you have V out equal to 0.63 V in. That's why I have the plot like this one here. Take a look at the plot between V and T. This is V out. At T equals 0, you have V out to be 0. Okay, so you start from here. And when the time passes by, you have the second term here decreasing. And when T is long enough, you ignore this term because it's very small. And finally, your capacitor, we have the voltage across it to be V in, same as supply voltage here, or in this case is the charging. Start from the voltage across C to be 0, and then when you supply the input voltage, when the time passes by, the voltage across capacitor increasing, and finally it's going to reach V in. Now take a look another plots. You still have R in series with capacitor, and you also have the source voltage to be V in. Let's put the input voltage to be your square wave. You notice here actually this I did wrong here. This is supposed to be V out or V across capacitor. When you have a supply input voltage, your capacitor start charging, so you have your voltage rising, and then when you don't have any input supply voltage, you see start discharging, so it's become like this, and back to V in again. When you supply input voltage, it start charging again, so it's going to be like this. What about a square wave like this? It's going to pretty much to be the same. So this just give you idea about how capacitor work. Okay, charging and discharging. As I mentioned before, from this equation, when your T is big enough, or in this case you can put T much greater than RC, or is about 5 times of RC, a rule of thumb, your V out finally is going to be equal to V in, as I mentioned above here. Okay, V across C start from 0, and then when the time passes by, finally you're going to have V across C to be equal to V in, the supply input voltage. Now if V are 0, you have no input voltage. Capacitors start discharging or Vout decaying in the term of exponential negative t over RC. Just give you an example. If you want to find the rise time from output voltage or the voltage across capacitor, 10% of the input signal to 90% our signal is equal to 2.2 RC. You can solve by yourself. So I put this one, just use a simple math, V out over V in for this equation here. You want V out to be your 10% of V in, or it becomes 0.1. You simply make it equal to 1 minus exponential negative t1 over RC. So I have exponential negative t1 over RC becomes 0.9. Simply, move this one to the left and move 0.1 to the right. Now you take a look at the 90% of the output voltage. Same V out over in equal to 0.9, so I put this one as the 1 minus exponential negative t2 over RC. You do the same thing. You have t2 equal to RC ln 10, and delta t simply t2 minus t1 is become RC ln 10 minus RC multiplied by ln R 10 over 9. And simply this one ends up to be ln over 10 over 10 over 9, right? So you end up with delta t equal to RC multiplied by ln 9. That gives you 2.2 RC. That means the time for the voltage, or 10% of the input input voltage to be V out to be 90% of the output, the input voltage. Now let's take a look at more complicated circuit. Sometimes you will see equation. I'm not going to prove this one here. When you want to find V out, you simply can calculate from this equation, 1 over RC, integration from negative infinity to any particular time, and V input tau multiplied by exponential negative t minus tau over RC, and then this is the tau. I put this wrong here because you need to end up with time, right? So you need to integrate with respect to tau. Let's take a look at the circuit here. You might see it's complicated and you're not familiar with that, but in the basic electronic 1 series 1 I already mentioned about Thevenin theorem. This is you consider this one as the load, and this is you have R1 and R2, and this part is simply become the source or the black box of the source voltage. What you can do is you can convert this circuit by using Thevenin theorem. Make it input to be only VTH, and then you have only R left to be RTH, and you connect the load to the circuit here. Easy to calculate, and it's back to the previous circuit, just like just talked. And RTH simply become R1 in parallel with R2. So that's why I have our RTH here become R1 in parallel with R2. And I actually repeat how to apply the Thevenin theorem to the circuit again. you still remember your RTH simply become R1 in parallel with R2, and this is your load. Next step that you need to do is you need to find V out, and V out simply you apply the voltage divider, so it's become VTH here multiplied by XC, and then divide by the total impedance, which is equal to RTH plus XC, when XC is the impedance of the capacitor. But at this point we're not going to use this equation, but we're going to how to use this equation here to find V out. Okay, let's bring up this equation, and this is tau. UVT equal to 1 over RTH multiplied by C, and then integration from negative infinity to any particular time t. V in tau multiplied by exponential negative t minus tau over RTH over C dt, d tau, sorry, just like you bring up equation down here. And if you have our input to be step input, you just simply put V in to be V0. Okay. And you take a look at this one. V in here become VTH. Everything is still the same. And now your VTH, you still have it here. What you need to do is just integrate, this term respect with d tau. I keep this still the same here. When I integrate this one, I have RTH multiplied by C. This is from integration. And for integrate of exponential function, you still have the same function. So I have this function down here. But when you integrate with respect to tau, this is simply become positive tau, or you can change the equation to be exponential of tau minus t over RTH multiplied by C. Okay, that's why I don't have negative sign here, and it still become the same. And you take the limit from 0 to any particular t, because when you're talking about a step function here, you have the input voltage start from t equal or greater than 0, so I don't need to put the limit from negative infinity. I just change the lower limit to be 0. So our next step, what you need to do is this one is cancel out. You have VTH here, and you have plug in tau become t. The first term you get exponential 0, so it's become 1. The second term is from lower limit 0, so you plug in tau to be 0. So you end up with the exponential negative t over RTH multiplied by C, and this is your output voltage, or the voltage across capacitor, where your TH is, you can use from the above circuit here. Actually it's become V open, which is equal to V in multiplied by R2 over R1 plus R2. You have RTH equal to R1 in parallel with R2, and R1 equal to R2 10k ohms, so it's become half, our total become half of 10k ohm. So This give you 5k ohms right here. And VTH, you simply plug in R2 equal to 10k ohms over R1, which is 10k ohms, plus R2, which is 10k ohms. So you simply have VTH become half of your V0, which is, this is your V0 input voltage. Okay, so you probably have some idea about how to calculate for voltage across capacitor. So when the time passes by, like this equation, and it exactly the same as we talked about in the previous page. Like this one. Let's see if we still have 300. Okay. The next application of capacitor for circuit is would call digital waveform generator circuit. When you connect circuit like this one, you have our CMOS as buffer and the other CMOS as a buffer. This is your input A, and then you have our input to the second CMOS buffer to be B, and you want to see your output as C. If I have input in the term of a square wave like this, you know exactly when the square wave pass to your CMOS, and this is simply that the circuit of capacitor in series with resistor that we talked about before. So your V out is simply become when you have the input voltage coming into the circuit, your capacitor still start charging. Okay, and finally it will reach at the maximum voltage, and that's the voltage going to be equal to V input, because this is buffer. That means you not amplify your input signal. And when your input, you have no input coming in, your capacitor start discharging, and it look like that one. What happened is that we call digital waveform generator circuit. It will delay your input signal like this one. Everything is going to be the same except it shifts your input signal by a certain amount of time. Look at this one, it shifts by 10 microsecond. Okay, so this is just give you an idea about what happened when you connect your RC circuit here between two CMOS buffers. You have your input voltage show up at the output. It's just like delay signal or delay digital signal. If you want to do that, you can apply this circuit. The next one is we're talking about the differentiators. You connect the circuit like this, R or C in series with resistor, and this is your V out. The same, you do the same thing. The current flowing through capacitor actually equal to our C multiplied by the VC over dt, and also equal to V out over R, because they have the same voltage level here. So V out compared to the ground divided by R, this gives you I. This is in circuit in series, I mean R and C, so they have the same current. And your VC is simply become V in, because V in is higher than V out. So use V in minus V out over dt. You rearrange the equation. You simply separate, two terms here. It's come out to be like this. Now for differentiators, if C and R are small, what happened? If C and R are small, when R small, this term is large. And this term is small, correct? So you ignore this term. You end up with this term and you keep this term. So C dV in over dt equal to V out over R, and you want to find V out. You simply multiply R to C dV in over dt, and that's why they call a differentiator, because you differentiate input to get V out. You look at the plot when you have V in coming here. You want to connect the circuit like this. You want to write V out. You simply differentiate. When you differentiate this one, when V in constant, it becomes 0. Correct? And for V in at the beginning here, you have the rising edge of the square wave. So when you differentiate this one, it's come up to be the straight line. And also here, it's become negative, so you also have straight line here. And this one you have nothing because it becomes 0, because V in constant. But for this part, this give you the output signal look like this one. And this part, it give you 0 right here. And this part is also give you the negative signal like this. Okay, so this the basic concept how differentiators work. Okay, if I have C to be 100 picofarad and I have R to be 10 k ohms, of course your time constant can find from R multiplied by C. So end up with 1 microsecond. You have input coming in. It's the same thing, just like above signal over there, above circuit over there. And you're going to have like for B, output across the R. So what happened is that you have a differentiator, and this part is give you 0, but because you have C here, and then it start charging quite a bit, and then for differentiator here you have no V out, so your V out drop down to be 0. At this part you have the signal look like this one, and also on the negative or the falling edge you have the signal down here. But in the real circuit, when you connect diode to the circuit, the diode is allowed the current flowing into only direction. So in this one, diode tends to get rid of the signal right here, so you end up with your output signal to be just like that square wave. And the circuit, we use that for leading edge detector. You detect any signal that's coming with the leading edge. Okay, so it's give you just like digital signal here. That's the application of differentiators. Now The other one is the for capacitor application, use the integrators. It looks pretty much like the previous circuit, except you have replaced C by R and you replaced R by C. You do the same thing. You have the current flowing to R and capacitor. So the current across capacitor is become C dV out over dt, and the current flowing through R here is simply V in minus V out over R. For the case that V out over V out much less than V in, so you ignore V out on the right side here, so you end up with dV out over dt is just about V in over R. You want to find V out, you simply do integration of V in dt, so you end up with integrator. Okay, this for example here, you have V in coming in, and then V in multiplied by dt is simply, like in the small section of your rectangular here, you add them up. Just it looks like you find the area under the curve here. So when the time are small, you have the small area, and then when the time pass by, you add up area together, so your area increasing. This give you V out. So it's just like integrator. That's the idea how the circuit work. And you have many applications for integrator circuit. Use that for control system, feedback, analog digital conversion, or even waveform generation. Okay, so this one is concerned about capacitor. Next, we have devices that are impedance also are frequency dependent, the same as capacitance or capacitor. This one we're going to take a look at inductors and transformers. Well, for inductor, you will have voltage across inductor equal to L di over dt. So you're going to have the VL when you have the current change with time. Same concept as capacitor. When you supply voltage 1 volt to L 1 Henry, you're going to have the current increasing 1 amp per second. Okay, just look at the equation. And the same as the capacitor, not like resistor. For the power dissipation, you have no power dissipation or no heat, but the energy will be stored in the term of magnetic field. So you get involved with the magnetic field. And for inductors, they have many applications for radio frequency or circuit, and also transformer. That's very important for electronic devices. For transformer, you have the symbol look like this one. On the left side, we call the primary side, and on the right, we call secondary side. And you have like coil here, and also you have coil here wrap around our magnetic core, and you don't have any connection between the primary and the secondary here. You can find V out over V in when you have V in coming here, and this is V out. V out over V in simply equal to number of turns on the secondary side divided by number of turns on the primary side. But when you consider the current, it's going to be inverse proportional. So this become N on the primary side divided by N on the secondary. So it's worked out different way here. If you have N out much greater than N in, you're going to have a V out higher than V in, but you will have I out less than I in. Okay, that's how a transformer work. Now take a look at the frequency analysis of reactive circuits, because we are associated with our C and L. Both devices become reactive, not resistive, not like resistor here. Let's say here is become frequency dependent, both V out and impedance. Let's take a look at our capacitor circuit here. When you have input signal equal to V0 sine omega t, and you know that omega equal to 2 pi f, you have frequency here. You have current flowing through the circuit. From the circuit, you can write down the current, or IC, equal to CdV over dt. And if you differentiate V, which is equal to V0 sine omega t, you have C and then V0, and then you differentiate omega t, you have omega, and this one become cosine omega t. Correct? This is your current. And if you notice the plot between voltage and the current, for voltage you start at t equal to 0, you have sine 0 equal to 0, so it starts from 0, where for the current it starts from 1. So that's why we call phase leading the input voltage by 90 degree. Talking about current phase will lead the input voltage by 90 degree. And you take a look at amplitude here. I amplitude, this is the cosine. Okay, you don't care about the function cosine, because function cosine gives you maximum 1 anyway. So your amplitude of your current is just simply become C multiplied by omega and then multiplied by V0. And if you take a look at this one here, you keep V0 the same, because you want to apply the Ohm's law, I equal to V over R. And for this case, since your R is not just already the real number, it's become complex number, so I would write this down as Z. It's become complex number. Okay. So it seems C omega V0, which is the amplitude of the current, it simply become V0 over something, and I put something, become 1 over C omega here. So it's look like the impedance of the capacitor. Let's take a look at the example here. When you have C equal to 1 microfarad, voltage equal 110 volt RMS, F equal to 60 Hertz, you have IRMS equal to 41.5 milliamps RMS. Okay, this is just the starting point. Let's get you into the frequency analysis of reactive circuits. Now look at the voltages and currents as complex number. Okay, if I put the cap up here just to imply that V, the voltage, and the current here are complex numbers. So you write down the complex number plane, you're going to have the real part and imaginary part, and you have the phase here. For example, if you have the voltage source to be V0 cosine omega t plus phi, you can even write down this one because they're write it down as V0 exponential j phi. Or this is complex number. You have real part plus imaginary part. And at this point, you want to have the term of the time, or to play around with the voltage, input voltage equation. You simply add exponential j omega t, and to get the cosine, you need to add, just pick up only the real part of the whole term here. Okay, because you're going to have the cosine omega t. So our Vt equal to the real part of V exponential j omega t. I put V as the cap, as the complex number here. And also It become the real part of I exponential j omega t. So let's take a look at the Vt equal to the real part of our V exponential j omega t. Exponential j omega t simply become cosine omega t plus I did something wrong here. Actually it's plus j sine omega t, because you multiply V later on. So you have V cosine omega t, the real part, and this become the imaginary part of your sine omega t. Okay, I will show you again. We have you can write down Vt equal to this, our real part of V multiplied by exponential j omega t. And then when you multiply, you have exponential j omega t become cosine omega t plus j sine omega t. Okay. Because this term is the exponential j omega t, is simply become cosine omega t plus j sine omega t, and you have V cap multiply, so you have this term here. Now you take a look at this part. Why it's become this equation here. When you have the real part of this is the real part, so you simply multiply the real part to the real part, so you have cosine omega t multiplied by V here. And for this one, you need to pick up the imaginary part of V, because V are for imaginary part you're going to have J, correct? When you have J multiplied by J, it gives you the real part, because we want the real part of the whole thing. But for this one here, why I have this term to be V multiplied by cosine omega t, the real part of V. So you're talking about something different. Okay, why I pick up this one? Because you get the real part, you need to pick up the real part of V cap multiplied by cosine omega t. You're going to end up with the real part. Okay. And for this one, you have J already, so you need to pick up imaginary part of V, because imaginary part of V cap is going to give you our J term, and then J multiplied by J is give you the real part, because you want your VT become the real part, you don't want imaginary part. Okay. And also the current, when you have the current, follow that equation. This term to be the same, cosine plus j sine omega t. So you do the same thing, you need to pick up the real part of I cap and multiply by the real number, so it gives you the real number. And then for imaginary part here, since you have j sine omega t here, you need to pick up the imaginary part which have j, so you multiply together, just give you the real number. Okay, so simply when you write down vt, you're going to have the real part of v multiplied by cosine omega t minus imaginary part multiplied by sine omega t. Okay, let's just for better understanding, let's take a look at the Ex equal to V equal to phi j. Okay, now you take a look at the example. When I have a V to be phi j, what happened? You pick up this equation here. You will see that your Vt is going to become the real part of R. Let's pick up this equation instead, sorry about that. You have V become 5j, right? You multiply by cosine omega t plus phi j multiplied by j sine omega t. And then when you pick up this one only gives you the real part, because it becomes negative 1 multiplied by 5, so you end up with negative 5 sine omega t. The same thing as you do is here. Let's start over again. If you pick up this one, the real part of cosine omega t, you don't have that, because for V you don't have the real part, you have only imaginary part, so this one becomes 0. And for this one, you pick up imaginary part of V, it's actually become 5, and then you simply multiply by sine omega t. That's why you end up with this term, and you have the negative sign here. Okay, let's see I have enough time or not. Okay, it's going to be a long talk, so I would like to stop right here, and we continue in our basic electronics series 3.